Welcome back to College Algebra. In this video, we're going to talk about quadratic functions some more. I think we'll probably finish our discussion of this. We'll actually move into some applications as well. But I want to start off by talking about the vertex formula. Now, the vertex formula is a formula for finding the vertex of a quadratic function. It has a fairly simple proof. It just relies on knowing this idea. So suppose we have a quadratic function that, say, its vertex is at 2, -1, right? And say it comes up like this and like this. So here are its intercepts, right here and right here. The question I would like to ask is, where in relation to its intercepts is the vertex? Horizontally, just horizontally. Well, you can see just by looking at it that it's halfway in between. So if I know the x-coordinates of these two, I know the x-coordinate of this one because I can just average these two. Well, where the x-intercepts occur is where ax squared plus bx plus c equals 0, right? Well, I know how to solve this. I can solve it for any a, b, and c we did in Chapter 1. That's how we got the... we actually solved them first by completing the square, but that's how we got the quadratic formula. These would be the x-intercepts, b squared minus 4ac over 2a. Since those are our x-intercepts, I can average the two, so negative b plus square root b squared minus 4ac over 2a plus negative b minus the square root b squared minus 4ac over 2a over 2. This will be the x-coordinate of the vertex. Now, this is easier to add together than you might think. These already have common denominators on the top, so negative b plus negative b is negative 2b. You add the positive square root and the negative square root together, they just go away. So you got negative 2b over 2a, and then divided by 2 over 1. So that's negative b over a times 1/2. So that just comes out to be negative b over 2a. And that's how we get the x-coordinate of the vertex. How you get the y value is just plug into the function. So it's a very simple proof to establish that this is a formula for the vertex of a quadratic function. So let's do one of the problems we were doing right at the end of last video, only using this instead. So this is based on problem 45 from our textbook in this section. We're looking at 6x squared plus 12x plus 1. Well, let's just do these things by hand. So I could complete the square to find the vertex, but we can just do it this way. Negative b over 2a. Now remember, negative b over 2a, it doesn't matter how the terms are placed. The a is what goes with the squared term, the b is what goes with the x term. That's never different. It doesn't matter if they wrote it 12x plus 6x squared, it's still whatever is in front of the squared term is the a. Whatever is in front of the x is the b. So let's see, this is going to be negative 12 over 2 times 6. So that's negative 12 over 12, or negative 1. So that's the x-coordinate of the vertex. The y-coordinate, f of negative 1, equals, let's see, 6 times negative 1 squared plus 12 times negative 1 plus 1. That is 6 minus 12 plus 1. That is negative 5. So the vertex is negative 1, negative 5. Its axis of symmetry then would be x equals negative 1. Be careful when you're doing problems that ask you for this. They will ask you for an equation, so make sure you include the full equation, not just negative 1. X-intercept and y-intercepts. You have a couple options. Y-intercept, of course, just set x to be 0, so the y-intercept is 0, 1. If you want to find the x-intercept, there's really two options. You can do 6x squared plus 12x plus 1 equals 0 and do quadratic formula. Or you can get the vertex form. You don't even have to complete the square to find it at this point. The vertex form is going to be 6 because the a's are the same in both forms. The vertex was at -1, -5, so x minus -1 is x plus 1, and then minus 5. So that's the vertex form. So you can set that equals 0. Add the 5 over, divide by 6. X plus 1 squared is 5 6. And then square root both sides. X plus 1 is plus or minus the square root of 5 over 6. I probably rationalize the denominator. Multiply top and bottom by square root of 6. Will get me x equals -1 plus or minus the square root of 30 over 6. Looks like a 36. There we go. 30 over 6. If I'd done quadratic formula, I would have gotten x equal -6 plus or minus the square root of 30 over 6. Because it's basically just this, but with common denominators. So let's go ahead and graph it. Our vertex, drag this over. This is a parabola. Our vertex is at -1, -5. -1, -5. And, I mean, we had the simple point of the 0, 1. Might as well use that. There we go. Save. If you wanted to find another point, you could just plug in something. I mean, you could plug in 1. 6 times 1 plus 12 times 1 plus 1 would have gotten you 19, I think. And that's on the graph, too. You know, 119. So, actually kind of confirms we did the right thing. And domain and range. Domain, as for all of these, is -infinity to infinity. The range would be -4 with a bracket up to infinity. Yep, domain of every quadratic function, still all real numbers. Alright, before we leave this and go on to some applications, I wanted to look at one more problem from this section. And that is, I wanted to look at one of these, which I'll zoom in a little bit, just a little bit. So determine the quadratic function whose graph is given. So we have this graph. We need to figure out what the quadratic function is that produces this. They tell us the vertex and they tell us the y-intercept. Well, from this, we're building a quadratic function, so the first thing you need to ask yourself is, what does the formula of a quadratic function look like? If it were a line, we'd say f of x equal mx plus b, but it's not. That's a linear function. A quadratic function looks like this: ax squared plus bx plus c, or the vertex form, a times x minus h squared plus k. And in this case, they gave us the vertex. So it's really a bit easier to use the vertex form here. A times x minus 1 squared plus 2. And all we have to find out now is a. The vertex isn't helpful anymore, because if I plug in those points for x and y, I get 1 minus 1 is 0 and 2. I get 2 equal 2, which is true, but it doesn't tell me anything. But that's what the other point is for. If you use this point, -10 equals a times 0 minus 1 squared plus 2. Well, that means a, because -1 squared is 1, so 1 times a is a, plus 2 equals -10. And then you know what a is, because a has to be -12. So then our function is -12 times x minus 1 squared plus 2. It does say to simplify your answer, so we should go ahead and multiply it out. So -12 times x squared minus 2x plus 1 plus 2. That's negative 12x squared plus 24x minus 12 plus 2. So that's negative 12x squared plus 24x minus 10. So that would be our answer. Negative 12x squared plus 24x minus 10. Let's do some application problems. We're going to start off with this based on exercise 9 from our textbook. This is almost a little easier than it might be because they give us a lot of help by how they drew the picture. So it says Farmer Ed, one of my cats is named Ed, by the way. Farmer Ed has 7,000 meters of fencing and wants to enclose a rectangular plot that borders on a river. See the river? If Farmer Ed does not fence the side along the river, what is the largest area that can be enclosed? Well, they helpfully say the widths are x, and then this is 7,000 minus 2x. We could have actually figured this out ourselves, because we only have 7,000 meters of fencing. So if I take away x for this width, x for this width, I only have 7,000 minus 2x left for the length. So, this is called a maximize or minimize problem because we are trying to find the largest value of something or the smallest value of something. And they're generally always done the same way when you're dealing with a quadratic function. We don't know if we're dealing with a quadratic function yet, but we'll see. Area of a rectangle, because we are trying to find area. Area of a rectangle is just length times width. They're helpfully labeled on the figure, so area is x times 7,000 minus 2x. So that's 7,000x minus 2x squared. And you'll see, this is a quadratic function. Squared term, x term. And if you think about it, it is facing downward, because it has a negative a. If you're facing downward, where would you find the maximum value of a downward-facing parabola? Right here. The local maximum, or the vertex. So finding the maximum of this function, I could do it in my calculator, but it's easier than that. I just have to find the vertex. And I have a formula for that. So if we do negative b over 2a, remember, a is what goes with the squared term. So b is the 7,000. Negative 7,000 over 2 times negative 2. That is going to be 1750, I think. Because that's 3,500 over 2. Which is, yeah, 1750. That is the x-coordinate of the vertex, which would be x was the width. We want the area. Well, I could find out what the length is and work from there. I could just multiply them. But also, I've got this formula for it. The area is 7,000 times 1750 minus 2 squared. No. The squared is on the 2. It's minus 2 times 1750 squared. So let's pull up the calculator. 7,000 times 1750 minus 2 times 1750 squared. 6,125,000. This would be, are we in meters? Yep. So this would be square meters. 6,125,000. And note, normally in a problem like this, you'd also want to find what the length is. So, I mean, that's not terribly difficult. The width of the rectangle is 1750. The length would be 7,000 minus 2 times 1750, which is 7,000 minus 3,500. So it's 1750 by 3,500 are the dimensions of the rectangle. Let's do another application. This is a very similar problem, but it's harder because we have to keep track of exact numbers. You really don't want to round off when you're doing a problem until the end, and sometimes that means you have to write more. That's going to be the case in this problem. So we have a track and field playing areas in the shape of a rectangle with semicircles at each end. The inside perimeter of the track is 1,600 meters, so the distance around the outside. So we know the distance around the entire outer edge is 2 lengths. So 1,600 is 2 lengths plus these curved parts. Well, that would be the distance around an entire circle because we got both halves. The distance around a circle is the circumference, which if we have the diameter like we do here, W would be the diameter of the circle. That is just pi W. And then we know the area of the rectangle, which is what we're trying to maximize, is length times width. So we can get this formula for the area in terms of one variable or the other by just substituting. So let me substitute away L. 2L equals 1,600 minus pi W. Divide by the 2. L is 800 minus pi over 2W. So this becomes 800 minus pi over 2W times W. And our A of W comes out to be 800W minus pi over 2 W squared. Note again, we have a quadratic function that is downward facing because of the negative A. And if we want to find the maximum value of it, which we do, we're just finding the vertex. So the width, basically the x-coordinate, which in this case our variable is w, so our w-coordinate, that would make that happen, is negative b over 2a, which is negative 800 over pi over 2 times negative pi over 2. I'm going to redraw that. 2 times negative pi over 2, which is negative 800 over negative pi. So I'm just going to write it as 800 over pi. That's the exact width. How do I find the length? Well, I've got a formula for the length. L equal 800 minus pi over 2 times 800 over pi. The pi's will go away, the 2 and 800 will get 400, so that'll be 800 minus 400, which is 400. So 400 meters, 800 over pi meters. So the dimensions would be 400, and we do a calculation of 800 over pi divided by pi. 254 rounded to the nearest hundredth, 0.65. 254.65. A more interesting problem is, what would it be if I weren't trying to maximize the area of the rectangle, but the entire field? It wouldn't be a whole lot different. All of this would still be the same, but my area function, instead of just being length times width, I would also have to take into account the pi r squared, because the area of the circle would matter as well. Well, if we plug in, the same thing we had before, we still have this 800w minus pi over 2 w squared. But we also have, let's see, w would be 2r, so r would be w over 2, plus pi times w over 2 squared. So that would be pi over 4 w squared. And if I combine these two terms, that would be negative pi over 2 plus pi over 4 would get me negative pi over 4. I get 800w minus pi over 4w squared is my area. And if we do our work again, negative d over 2a be our w coordinate, or width. This would end up being negative 800 over 2 times negative pi over 4, which the 2 would still reduce, but now I still have a 2 on the bottom, so that would multiply times the top and get me 1600 over pi. So that's interesting enough. I mean, it's just double what we got from the other case. But look what happens if I plug into the length formula. Length would equal 800 minus pi over 2 times 1600 over pi. We get 800 minus 800 equals 0. And a natural question would be, how can it be 0? We want to maximize the area. Well, we do. And the truth is, a circle is the most efficient container of two-dimensional space we can come up with from this shape. So it's the best use of our 1600 meters if we want to contain as much area as possible if the rectangle just doesn't exist and we just have a really large circle. So that's why it comes out this way. You can fit the most area inside if it's just a circle. Let's do one more problem, and then we will call it a video. The last one we're going to do is based on problem 13. Here we've got a suspension bridge with weight uniformly distributed along its length, has twin towers that go up 80 meters and are 800 meters apart. So we draw the ground here. We have these towers. They go up 80 meters. And they dangle cables in between them, and they're parabolic in shape. The cables touch the road surface at the center of the bridge. So, let's see, about halfway in between them is right here. So, something like that. So that's the parabola, roughly drawn, of course. This distance is 800 meters. We want to find the height of the cables at a point 200 meters, so basically right in the middle. You might think they're 40, but it's not because they're curved. If they were straight lines, you'd be absolutely right. They would be 40 meters up halfway along. Since they're curved, they're going to not be that. So, how are we going to find the height? Well, the thing is, it's a parabola. We can come up with a formula for a parabola, and if we come up with the formula for the parabola, we can find the height of the cable at any point, the height of the parabola at any point. So how do we find this? Well, first off, we kind of need to figure out where our axes are going to be. Just for convenience, I think I'm going to put them here. So this point then is 0, 0. The reason for that is that's the vertex, so then I can use my vertex form. And it's pretty easy to use because just the h and the k are both 0. So we just have f of x equal ax squared. And I have these points, which, are 400 meters out from the center, so 400, and we know they're 80 meters up, so 480 is the point. We can just plug those in. 80 equals a times 400 squared. So a is 80 over 400 squared, and that's the formula. F of x equal 80 over 400 squared times x squared. So we have a formula for the parabola. All we got to do now Find the height of the cables when we're 200 meters from the center. Easy enough, just plug in 200. F of x is 80 over, not 800. 80 over 400 squared times 200 squared. Which, I could plug this into the calculator, but these are both squared, so I can do this trick. 200 squared over 400 squared is the same thing as 80 times 200 over 400 squared. 200 over 400 is 1/2, so it's 80 times 1/2 squared, which is 80 times 1/4, which is 20. So this point, when we're 200 meters from the center, is 20 foot off the ground, comma, be 220. So the answer is 20. That's going to be it for this section. Next time, we will leave quadratic functions and talk about quadratic inequalities. After we're finished with that, I think that'll just be one video. We will move on to talk about polynomial functions in general, which we've been hinting at for quite a while now. See you then. Have a great day.